This is version 1 of my reaction wheel. This is version 2. These are a bunch of others. And this is the final functioning version. Here's how I built it. So version 1 was based on this reaction wheel by James Burton. I chose it because it was the coolest looking one out of the ones I've seen. The only problem with the design was that the motor, the Eagle Power LA 8308, cost over $70, and I didn't want to spend that much just to learn how to do PID. So I naively believed that a cheap BLDC motor would suffice, and I modified the design slightly to accommodate for it. Spoiler alert, it didn't work. But why? Well, a couple of reasons. Reason 1 was that the motor just didn't have enough torque to do anything, and reason 2 was that the base was just way too big for that little motor to do anything too. This would also come into play later on as well. So version 2 was modeled after this reaction wheel by Nikodem Bartnik. His design looked a lot simpler, so I decided that it should suffice. I changed the design a little bit, bringing the horizontal supports from version 1 over so that it would not tip over as his did in the video. The motor he chose was the Nidec 24H. It had a lot more torque than the motor I chose, and it was a pretty common motor choice for reaction wheel projects, but I decided to reuse that same BLDC motor. Why? I don't know. Anyways, when it came down to testing it, after spinning it up, it seemed like it did generate enough torque to pivot the base, but I didn't have enough safety features in place, so when it spun out of control, it destroyed itself. So by this point, a lot of time had gone by, and I didn't really have a lot of progress to show for it, so I decided, you know what? Let me just get a design that works. Let me get a motor that works and just copy and paste that one-to-one so we can move on. No more design, no more bullshit. Let's just recreate the thing one-to-one so that we can get to the thing we actually wanted to get to with this project, which was understanding PID control. So that's what I did. This led me to the final version of my reaction wheel, which is based off of Rem RC. I chose his version because it looked incredibly simple to make. That rollaway effect that version 2 had wouldn't happen here, and the design just looked cool, so I decided to go with that. As intended, the design was not an issue. I made some slight changes to accommodate my motor and where I'd mount the MPU 6050, but it came out looking great. Really simple print job. The issue this time around was motor issues. You see, the chosen motor for this design, as with Nikodem's motor, was a Nidec 24H motor. The problem was that it came from China. The other problem was that I ordered it around Christmas time. I'm not sure if it's related, but because of that, the 1-week delivery time that was promised became almost a month. Because of that, I couldn't do anything for nearly a month as I waited for the motor to get here. And when the motor did get here, it was damaged, and it came with 12 pins instead of the 8 I was expecting. Really gotta read those descriptions. I tried to fix it up a little bit, and I accomplished that, but when I tested it out, I hooked it up to a 24-volt power supply, but it can only run on 12, so it didn't work. There goes a month. So I ordered again, this time ordering 2 just in case one arrived damaged. These ones arrived in a week. The first one arrived damaged. Something was wrong with the rotor, it was very hard to turn, and it wouldn't power on. But thankfully, the last one I got did work. Port terminals were still slightly damaged, but it was good enough. It made a solid enough connection, so I was able to hook it up and give it a test. Smooth sailing from here on out, right? No. Unfortunately, I had not taken enough due diligence to keep my wires away from places they shouldn't be touching. So my 24-volt power supply wires touched my Arduino wires during testing, and my Arduino caught on fire. Unfortunately, I do not have any video of that, but it was pretty terrifying to say the least. So, $20 and another Arduino later, we can finally test it. How'd it go? Okay, but it could be better. The motor would spin and spin, but it wouldn't spin enough to do any pivoting. While holding the frame and turning the motor off or changing the direction, I could feel a reaction torque, but that reaction torque just wasn't enough to pivot the frame. I figured it was probably because, like the first one, the frame was too big, so I shrunk the frame size down. Same for the wheel. Tested again, and baby, we had some movement. Now we can get to the code. I won't bother going through all of it because it's pretty long, but if you like a detailed breakdown of the code and a step-by-step of how to recreate this project, let me know in the description and I'll make that video. So, PID, the whole point of this project. What is it? It's a control algorithm. P stands for proportional, I for integral, D for derivative. Let's start with P. P, the proportional, looks at the current error. In this case, how far away you are from the target angle, which is upright or 0 degrees. The larger your error, the larger the proportional term's contribution to the output. For example, if you're 10 degrees off and your P gain is 5, that's 5 times 10, so your output is 50. If you're only 1 degree off, that's 5 times 1, your output is 5. The closer you get to 0, the less the proportional term pushes back. When tuning, you want to increase your P gain until the reaction wheel starts to oscillate. That's how you know it's large enough. But oscillation is exactly the problem. The wheel is overcorrecting back and forth because P only sees where you are, not how fast you're getting there. That's where D comes in. So D, the derivative term, looks at how fast the air is changing from one moment to the next. Think of it like a car with no shock absorbers. It'll bounce forever. D is your shock absorber. So, if your angle is changing at 20 degrees per second and your D gain is 2, the D term contributes 40 to the output to break that motion. When combined with P, the D term dampens the oscillation and settles the system down. That leaves I, the integral term. Where P looks at the present and D looks at how fast things are changing, I looks at the past. It accumulates your total error over time. So if the reaction wheel keeps sitting 2 degrees off, that error keeps building up until the algorithm pushes hard enough to fully correct it, essentially wiping out that small persistent lean that P alone can't fix. If that didn't make any sense, then read this explanation from Reddit. It's really solid. The result is a mostly working reaction wheel. There's definitely room for improvement, but I just wanted to learn more about PID, and I accomplished that. So, phase 1 of the road to building a guided rocket is complete. Next, I will resume work on the flight computer. That should come out in maybe a month, maybe 2. We shall see.